ideal length of these, the stripped portion on the end of each wire is probably, I would say, sort of 5 to 7 millimeters, right? So these are millimeters on the ruler here. You can see that the silver bit of stripped metal on the end of the wire I'm holding there, it's just over 6 millimeters. Now you don't want it to be much more than that, right? If the metal is way too long, then when you plug it into the breadboard, you're going to end up with metal exposed at the top. So I'll just show you what that would look like. Balance something. It's Ireland's most expensive paperweight there. I maybe ask some people have just kind of carelessly stripped off like more than a centimetre on the end. When I plug this into the breadboard, so let's say I'm plugging this into one of the rows on my breadboard here, I've plugged that all the way down into the breadboard, and you can see that there's still quite a bit of metal exposed there. Now the problem is that if you've got a lot of wires on your circuit that are like that, there's a very high probability that some of these exposed metal parts are going to end up brushing off other bits of metal, and you get short circuits and things burn out. Now the other temptation that some people have is if they cut it off too long like that, they try and kind of like coax it inside the breadboard like this, right? So I've just kind of shuffled in that extra wire all the way inside the breadboard. Now the problem is that wire is kind of snaking around inside the breadboard trying to find somewhere to come to rest, and the danger is that it'll find its way and touch some other wire that it shouldn't be touching. What you really want is more like what I have on these nice short wires here. So that's about 6 millimeters there. When I plug that in, it just goes cleanly all the way to the bottom. So I know I can feel that it's being held underneath by the metal clip, but the plastic is covering the metal all the way to the plastic surface of the breadboard. So we have a nice stable connection there, and there's no chance of a short circuit occurring. Put this back on here now. The colours that we use the most, and the reason we use them the most is that they represent the positive and negative supply voltage in your circuit. So in this circuit, black will represent 0 volts and red will represent 6 volts. And the reason those are the voltages is that's what's coming out of my battery pack here. It's a 6-volt battery pack. So on the breadboard, I'll just begin by connecting up the battery pack. And I'm going to connect the black wire to the rail on one side and the red wire to the rail on the other side. So you can see there's my battery pack connected onto the breadboard, and you can see I've chosen to make this rail here 6 volts all the way along there. And similarly, I've chosen to make the lower rail here 6 volts all the way along here. Sorry, excuse me, 0 volts all the way along here. So the blue line there. The lines on the breadboard are there to remind you that that's one single continuous connection. When you use larger breadboards, which you'll see in due course, they can have slightly different configurations of the rails around the edges of the breadboard, and they often include coloured lines like this just to tell you exactly how they're laid out. The centre sections though are almost always the same. It's rows of either 5 or 6 short rows of 5 or 6 holes which make a single connection. If you look carefully, what's underneath each row of holes is a single metal clip, and it's got a few sort of metal sort of finger grabbers. When you put a wire in through the top of the breadboard, it's getting held underneath by that metal clip. So when two things go into the same row, they end up getting held by the same metal clip, and it provides one continuous conducting path from one to the other. So that's how it works. Okay. So I'm going to build my circuit on the breadboard here directly with the sensor. And it's not the only way you can do this, but that's the way I'm going to do it. So So I've plugged it in here. You can see I've got 2 of the legs are here plugged into rows on one side of the board. So I have it in, what is that, rows 9 and 12. A little bit hard to see, so I'll just try and point it out. So that's one leg going into row 9, and that's second leg going into row 12. So that's on one side. And you'll notice if you look carefully on one side of the sensor, you can just see the name of the component written on it there, TCRT 5000. I should have mentioned, by the way, these sensors are very adaptable. You can use them for lots of different things, but they're also phenomenally cheap. So they cost about 10 cents each. So it's a good sensor. And there is a kind of a chamfered corner on it. So they provide some sort of markings which you can reconcile with what you'll see on the data sheet to figure out which legs are which. Now, hopefully I have it the right way around. So Okay, so the first thing I'm going to do is I'm going to connect 6 volts to the top of each of the 2 components. Now, in fact, just it so happens that the way around it is here, the blue eye is on the right and the black eye is on the left, but otherwise the circuit is going to be the same as it was. I'll have that over 1 row too further. And then I'm going to connect resistors from there down to ground to complete the circuit. So for the LED, I've got a 220 ohm resistor here, and I'm going to connect from the other leg of the LED down to the ground rail there. And then for the black eye, I'll put in the larger resistor, the 10k resistor, and I'll connect from there down to ground. Okay. Now just to remind you what the circuit diagram looked like there, bring it back. So you can see on the circuit diagram we had 2 legs basically on the circuit. There's this one here, the LED, and this one here, the phototransistor. So on my breadboard circuit, I have the same 2 legs. They're kind of the opposite way around in that the LED is now on the right and the phototransistor is on the left, but otherwise it's the same circuit, right? Now you can also see, if you look carefully there, you see the pink light coming out of the LED? Yeah. That's the infrared light coming out. So you won't see anything if you look at it. Like I can't see a thing looking at it. It looks like it's switched off, right? But when you look at it through a camera, in a lot of cases you will be able to see it. Doesn't look all that bright because the camera is not designed to actually pick up infrared, but it is sensitive to it to some extent. So you'll be able to see that the LED is actually working. So that's a good sign. It shows us that we have things more or less hooked up in the right way. Now the next thing that I want to be able to do is to see how the voltage is changing at this point here in the circuit. So this point in between the phototransistor and the 10 kilo ohm resistor, because it's really the voltage that's generated across that resistor there. That's what we're interested in, because that's the voltage that changes when the amount of light reflected onto the phototransistor changes. So like this, or there's ones in the lab downstairs, you'll see that they can be a little bit complicated looking. They measure lots of different things. So for example, this one here measures not just DC voltage but also AC voltage and current and a few other things, right? Now what I'm going to do is I'm going to set this to measure DC voltage up to a maximum of 20 volts. And where it's measuring that voltage is in between these 2 wires here, so my black and red wires here, and I've connected single core wire onto the end of the probes just so that I can plug them easily into the breadboard. And hopefully we'll be able to see this while I'm doing it. So I'm going to connect the black wire onto the circuit on the bottom rail there. So this that's the black wire of the multimeter plugged into the ground rail, just along the bottom here. And then I'm going to connect the red one here so that I'm measuring the voltage across that resistor, the 10 kilo ohm resistor. That's brown, black, orange. And we'll look at the voltage here. Now I just want to try and tip this a little bit on the side because it's picking up a very strong reflection from above. Okay, so it's currently measuring 0.4 volts. Now if I bring in something like, even my thumb there will reflect a good bit of light back into the sensor, you can see that the amount of current allowed through the phototransistor is changing quite dramatically, and when that current goes through the resistor, the 10 kilo ohm resistor, the voltage goes up, right? So if I move my thumb in closer, it gets a better reflection. Now my thumb wouldn't be like a perfect infrared reflector, but it is kind of a pale coloured object, so it will tend to reflect it a little bit better. If I use something white, maybe like if you use something white, like white paper, this would be a very good reflector of infrared light. So if I bring this over to the sensor, we should see the voltage go right up. So you can see you're up to almost the full battery voltage there. Now it's a good idea to set up this experiment yourselves and see how high the voltage goes, but also to get a sense of how quickly it goes down as the thing it's reflecting off moves away. So I'm about maybe 15 millimeters away there, and I'm already down to half the response. If I go another couple of centimeters out, you can see it's still getting a reflection, but it's tiny, right? So if you were trying to detect this in your program, you need to be sure that that sensor is very close to the surface that you're detecting from, right? If I was to put something black up in front of it, I might try it with this battery pack. You can see, even though the black object is very close to it, it just doesn't reflect enough light, because the whole thing that makes it appear black is that it's absorbing a lot more photons rather than reflecting them. The reason this looks bright to us is that most of the light that hits it reflects straight off it and it goes into your eye, and so actually it looks quite bright. Black objects are basically the opposite. They absorb much more of the light that hits them, so they don't appear as bright to our eyes. And same thing applies here. It just absorbs the infrared light and it doesn't come back and hit the phototransistor. So, what are some important messages to take away from this? Well, firstly, there's the actual circuit that you can build to get the color sensor working. There is an article up on the blog as well, which explains a bit about the theory of the infrared reflective sensor. What I will say is you're going to be relying on this in a big way for the two main tasks that you do in this module, the race to the wall and for the Sumo. So understanding how the color sensor works makes you much better equipped to diagnose and solve problems that you might encounter with it. And if you have unreliable color sensors, that can really plague your development later on when you're relying on them to guide the robot. Really, most of the decisions that your robot makes and how it's going to remain on the table at the end is down to having reliable information coming from the color sensors and making good use of that in the program. It's the primary means that your robot will sense its environment, is just by using these sensors here. So for you to understand them and be able to diagnose them effectively is going to be very important. Now, I don't have time to do a full example on the Arduino with the output of this, but I will just give you a couple of pointers in case you're at the point where you want to read the signal out of this on the Arduino. I would say don't just build the color sensor and plug it straight into the Arduino and try and get everything working at once. A big aspect to successful fault finding is trying to break a complicated system into simpler subsystems that can be tested individually. And you here have got a sort of a self-contained subsystem that you can build and test using a multimeter completely in isolation from the rest of your system. So you can know that this bit definitely works before you try and rely on it to do something else. Even within this system, the fact that the LED and the phototransistor form kind of two separate halves of the circuit mean that you can fault find the LED part on its own just by checking if there's light coming out of it with the camera, and then once you're sure that's working, then you can go on to look at the other side here. So when you're fault finding, you need to be able to break things down into simpler parts that you can test individually, and this is a good example of when you can do that. However, with the Arduino, let's bring up the Arduino here. Now you'll find some examples in the Arduino under the file menu and under examples, and if you look under, I think analog input will probably give you sort of a good starting point here. You'll find sample code for lots of different things that you can do with the Arduino in the menus at the top here. Now, I'm not going to use most of this, I just want to strip it down to the basics for the moment. And I'm going to imagine that I have maybe an LED connected to D3, I think that was what I was using last week. Now on one side of your Arduino, I don't have an Arduino here with me, but along the two sides of the Arduino, the pins are labelled on the top surface of the Arduino Nano. Let's just see if I can pull up the picture here. Actually, probably don't have time to do that. But you'll notice that one of the pins is A0. So there's A0, A1, A2, and so on up to I think A9. So I'm going to read the voltage from A0. So the way that we would do that is just as I've shown here. I'm going to take this stuff away, but I'll leave sensor value here. So I'm going to use a variable called sensor value. So this int sensor value, this is going to allow us to store a number, and down here we're going to read that number over and over again by reading pin A0 using the analog read function. It's going to give us back a number that we store in here, and the voltage range from 0 to 6 volts is going to give us a value between 0 and 1023. Okay, now that's 2 to the power of 10 minus 1 because it's a 10-bit value. We will return to that in the near future. And if you wanted to do something like, you know, switch a motor on and off depending on the color under the sensor, you would do it as follows. If sensor value, so the number that we've just read from A0, which would be the output of your color sensor, is greater than, and I'm just going to pick a number halfway between 0 and 1023, so that's 512. So if the sensor value is greater than 512, I'm going to do one thing, and if it's less than 512, I'm going to do a different thing. So what you actually do here is up to yourself, but I'm going to, let's say I'll switch pin D3 high in one case, and I'll switch it low in the other case. So if that was switching a motor on and off, then we would see the color under the color sensor would now be switching the motor on and off. Now you can put in a delay here or not. You don't necessarily need to have it for this example, so just take that out there. Okay, so that'll be a real simple example of how to record the input from your color sensor. So the voltage that come out of your color sensor circuit, you would plug that into A0 on the Arduino, and this analog read function here just allows you to measure the voltage on that pin between 0 and 6 volts. It'll turn it into a number between 0 and 1023, and that number will be stored into this variable here. And then I've used an if-else statement here to choose between two different instructions that I could do based on whether or not the sensor value is greater than 512. Because this is in the loop function, it makes the same decision over and over and over again. Now, as I say, I don't consider this a full example, but it's just to give you a sort of rough idea how you would do it. So we'll probably come back to this, I'd say, next week to make some more decisions based on what's coming out of the sensor. Okay, I think we're pretty much out of time there, are we?